Hey guys, welcome to the EEE 202 midterm review hosted by the FSC Tutoring Centers. I'm Vibhas and I'm an executive tutor at the tutoring center. And I'm going to go over some of the concepts that you may see in the midterm, whether it's this week or the next. So let's get started. Over here, I'm going to go over a few conceptual questions, which you can see on your screen. Um, and let's work through these and try to understand what concept they're trying to talk about. So in this question, we have in the first question, we have an ideal current source. An ideal current source is one that ensures that a constant current keeps flowing through the circuit at all times. So if the current source has a value of 5 amps, it's going to keep pushing 5 amps no matter what's connected to the circuit. Whether I add more or less resistors, it's still going to be pushing those 5 amps. The way it achieves that is that this voltage across the current source, let's call it VCS, it is not a constant voltage. It's going to change in accordance to what the circuit is so that it maintains a 5 amps flowing out of this current source. The same thing with a voltage source would be that the voltage source's current, let's call it IVS, is not constant. It is whatever value it needs to be to maintain a 10-volt difference between the bottom node and the ground and the top node. So in this case, when the voltage value is 10 volts. Okay, moving on, let's look at this question over here. So it asks that if the resistance of the variable resistor, a variable resistor is a device which allows you to change the resistance during runtime. That means at if I have the circuit attached to the resistor where the resistance was set to 5 ohms, while the circuit's running, I can also change it to 10 ohms or maybe even higher, depending on what the device is capable of. So it's asking if I do change the resistance of the variable resistor, what happens to the brightness of bulb A and that of bulb B? So one important point to remember is that the brightness of the brightness is proportional to the power consumed by the bulb. And remember that in a single loop like this, the power consumed by the bulb is going to be I squared R. You might have seen other formulas such as V squared over R. So V squared over R would be the voltage across the bulb over the resistance. The voltage across the bulb in a series circuit is not easy to find, but the current across the bulb is very easy to find because we are looking at the same current in the whole loop. So we're gonna prefer using this formula over here. So I squared R, right? And remember that even if we change the resistance over here, let's say it was a 5 ohm resistance, we make it a 10 ohm resistance now, the current flowing through the circuit is determined by this current source over here. It's gonna stay the same. The brightness of the bulb is proportional to the power consumed. The power is the current squared times R. Therefore, we know that since the current's not changing, so let me say no change, that the brightness of both the bulbs in the circuit are going to be the same because the current flowing through them is not changing. So, so another way to think of that is that when we increase the resistance over here, the voltage that was present across this current source over here is going to automatically increase so that the current doesn't change. So it might go from 10 volts to 15 volts to try and compensate for the increase in resistance. So when you're writing your answer and it asks you to explain clearly, you may want to discuss that the current source automatically adjusts its voltage to maintain the current flowing at a constant rate. Okay, let's move on to the next question. So for the next question, we have an old-fashioned electric coil stub burner is pulled out of its socket. If the voltage, which would normally have, if the voltage is turned on to high, what would the voltage be across the empty sockets? So it's saying that a stove burner, you might have seen one at home like this, is pulled out of its sockets. So all it's left is empty terminals. And if you turn the dial on to high, what that means electrically is that you're applying the maximum voltage you can. And in the US grid, that would be 240 volts RMS. So the RMS stands for root mean squared. So remember that these are AC voltages being applied. The root mean squared is a way that we can categorize these values so that we can compare between different sine waves. So 240 volts RMS, the formula for the RMS voltage is the peak to peak voltage over root 2. So if this was the peak to peak voltage, the RMS voltage would be that divided by root 2. So the answer to this question would be 240 volts RMS would be applied. If they ask you to explain clearly, they're trying to understand why that even with no current flowing, so the circuit's broken right now, but we're still applying a voltage over here. Let's say we have a battery over here. We're still applying a 240 volts RMS. Why? Why would it have that value? It's because voltage still exists across open circuit terminals, but current does not exist. So the current value in this terminal is zero. Remember that. The third question is asking us about an ideal incandescent light bulb. The current going through it is doubled. So this is your light bulb. The current going through it is now double the current that was going through it. What is the power dissipated in that bulb? So originally, the power dissipated would be I times R. The resistance of the bulb does not change with the current flowing through the bulb. I square R, I mean. However, now the power is going to be I dash squared R, which is, and I dash is 2 times I. So it's going to be 2I squared R. So the factor of increase from the original power would be 4 times, not twice. Therefore, the power dissipated in the light bulb is not doubled. It's this statement is false. The explanation would be the math that we have done over here. All right, let's move on to some more concepts over here. Let's move on to node analysis. This is a very common method of analysis you can use to solve circuits with many resistors and many sources. So there are 3 steps I would encourage you to follow when you're doing node analysis. The first step is to name each node as we have done over here. So we have 5 nodes over here. V1 over here, V2 is here, V3 is here, V4, V5. The way you recognize a node is that it's going to be an unbroken stretch of wire. It doesn't matter if it forks out. It could fork out, but it's just got to be unbroken. So all of this is the node V2. We also need to assign one ground node. So one ground node, you can choose any node of your liking. Usually you choose the node which is closest to the bottom of the circuit. So in this case, it's over here. We're going to make this the ground node. What a ground node does is it's just telling us that we are considering this node to have 0 volts. So ground is 0 volts. We have our 5 nodes. So we have 5 unknowns, the node equations. Therefore, to solve this, we need 5 equations. The question asks us to solve the circuits, to write down all the equations needed to find I naught. So let's do that now. So I naught, if you just look at the circuit, it flows the left, from the right to the left. Therefore, following passive convention, I naught is going to be V3 minus V2 over 9 ohms. So we already have an equation for I naught, but there are two unknowns over here. We don't know what V3 is, and we don't know what V2 is. So let's start writing our node equations. So let's write down the equation for V1 first. So in the node V1, if we apply KCL, the current entering this circuit, it should be the same current leaving the circuit, or all the currents leaving the circuit should add up to zero. There's a current going up, there's a current going to the right. We don't know what the current going to the right is just yet, nor do we know the current going up. So in this case, actually, we are not going to use KCL. We're just going to use this source over here because it's a voltage source. So this is a voltage source. It's telling us what V1 is already. So V1 is equal to 3Ix. We don't know what Ix is, but we can write down an equation for Ix. Ix on the circuit is over here. Using passive sign convention, it's going to enter a resistor into the positive and exit through the negative. And it looks like it's 0 minus V4, 0 at the positive minus V4 at the negative, over the value of the resistor, which is 7 ohms. That is the same thing as minus V4 over 7 ohms. So we can say that V1 is just equal to 3 times V4, negative 3 times V4 over 7. So we have one equation over there. So let's try to do the next equation. All right, let's have a look at where V2 is. V2 is over here. We got to consider all the currents entering and leaving the circuit, entering and leaving the surface, V2, right? So there's one coming in over here, that's I naught. There's one coming in over here, and there's one coming in over here. So all the currents that are coming in are gonna be adding up to zero. So let's write that down. So let's account for this one first. V1 minus V2 over 7 ohms plus V3 minus V2 over 9 ohms, which is I naught coming in from this way, plus whatever's coming in from V5. V5 minus V2 over 2 ohms, all add up to zero. There you go. That's our second equation. Let's write our third one. The third equation is going to be centered around V3. Now notice that between V3 and V4, we have got a voltage source. The difference between this voltage source and the one we had for V1 is that this is a dependent, yeah, and this is an independent source. So an independent source has an unknown amount of current flowing through it. We can never know how much current is flowing through the independent source. So we're going to do something. We're going to make this surface contain both V3 and V4, which is the nodes on either side of the independent source are merged into one, and we call this a supernode. So now when we write our equations, we're considering all the currents that are coming in and out of this larger surface, not just the surface containing the single node. But luckily, we also have an equation that relates the two voltages. So we know just by looking at this that V3 is 4 volts greater than V4. So V3 minus V4 is 4 volts. That's the third equation we got. The fourth equation we can say is centered around the supernode. So Let's try to account for all the currents. There's I not leaving. So V3 minus V2 over 9 ohms again. That's leaving over here. Now there's two currents leaving at the bottom. So there's a 6 amps coming in. So negative 6 amps is leaving, right? And then we have this leaving over here, which is V4 over 7 ohms, which is negative IX. All of these add up to 0. So that's our fourth equation. For our fifth equation, we're going to look at V5. There's current coming in here, there's current leaving here, and there's current leaving here. So we got to make sure that all of them are facing the same direction, all the currents coming in and going out. So let's just consider all the currents that are coming in. So they got to add up to 0. So 5 amps coming in, 6 amps leaving, so negative 6 amps coming in. Then from the top over here, from V2, we're getting V2 minus V5 over 2 ohms. All of these add up to 0. We have accounted for all of them. So these 5 equations are the solutions to this question. If we plug these 5 equations into a calculator, we can, in the matrix form, using RREF, we're going to be able to solve. Or we could also hand solve these by substituting the values we know, like V1 or V3 and V4. But if you could reach this step, you're pretty much at the end of the solution. Okay, let's try one question on mesh analysis. It's really similar to node analysis, except meshes are these loops in the circuit. So if I have a circuit like this, we have one loop inside, but we also have this loop outside called an outer mesh. The outer mesh is always in the opposite direction of the loop that is inside. And in most cases of mesh analysis, we're going to say that the outer mesh doesn't exist because we say it's a ground mesh carrying 0 current. Okay. All right. So I have already marked out the meshes in this circuit. So there's one, two, three inside, and then there's the outer mesh. For the purposes of this problem, we're going to consider that the mesh in this section of the circuit is the ground mesh. Okay. A ground mesh is one that internally carries 0 current. It might not, but for the purposes of solving this question, um, we're going to consider that to carry 0 current initially. All right, so let's try to solve this question. So it's asking us to solve for the power dissipated in the 4 ohm resistor, right? So the power dissipated in the 4 ohm resistor, which is over here, is going to be I3 minus I1 times 4 ohms. That's because I3 is going this way, I1 is going this way. They're fighting against each other. So the current that's actually flowing through is going to be the difference between I3 and I1. We're going to square that and multiply it by the resistance. That's the formula we know for power, I squared R. The current flowing through the resistor is I3 minus I1. That's being squared, being multiplied by the resistance. That's going to give us the power. So we know the formula for that, but we don't know what I3 and I1 are. So these are our unknowns. So we have 3 unknowns in this question, so we need 3 equations to solve it. And these 3 equations should be unique. They shouldn't be telling you the same thing again. All right, so let's start writing our equations out. So in the mesh I1, since this is 0 over here, the current flowing this way in this mesh is 0. So we can say that I1 is equal to negative 8 amps because because we have this current source over here that's setting the value of I1 to negative 8 amps. It's going against I1. So we have drawn I1 going clockwise. So as it's going against I1, we're going to say that it's negative 8 amps rather than 8 amps. I2, let's see what we can gather from I2. We know that I1 is going this way, I2 is going this way, and this current source is giving us enough information to know the relationship between both of them. And it seems like the difference between I1 and I2 is 1 amps. And I1's winning in this case because I1 is more than I2. That's why 1 amp is flowing downwards. So we have the difference between I1 and I2 is 1 amps. So we can just say that I2 is equal to I1 minus 1 amp or 1. That's our second equation over there. For our third equation, so let's actually solve this out first. I1 is negative 8. And if we subtract 1 from that, it's going to be negative 9 amps. So I2 is negative 9 amps, right? But we still have to find I3. So let me just double check my calculations here. We have, yeah, that makes sense. Okay, let's see. Now for I3, we have this outer loop over here. We're gonna add, so we're gonna follow KVL, add all the drops, voltage drops or rises in the closed surface, in the closed loop. So in this case, the closed loop is the outer loop over here. So we're gonna add, so let's say I3 is flowing from the left to the right of this resistor. So it's like that. Here's from the right to the left, here right to the left. So 5 volts plus I3. So it's these two are in the same direction. So I'm adding them. Plus I3 times 8 ohms plus I3 minus I2, since I2 is going against I3 in this case, times 1 ohm plus I3 minus I1 times 4 ohms. I3 minus I1 times 4 ohms. That's the drop over here. All of these drops add up to 0. So all the drops and rises add up to 0. That's what KVL tells us, and we're going to apply it. Now we know what I1 is, and we also know, sorry, this should be a positive. So wait, I1 minus 1 amp. Hmm. Right, okay. Yeah, we know what I1 and I2 is. So we can just replace those values into wherever we see them. All of the other terms in this equation are numbers. So we can find what I3 is pretty easily. I'm not going to solve it over here. I'm going to leave that as an exercise for you. But you can clearly see that the solution of this equation is going to give you what I3 is. Once we know what I3 is, you can plug them back over here and here to find the power dissipated in this resistor. All right, let's go over superposition. What does superposition tell you? Superposition is a way to kill all sources but one, and analyze the circuit with just that source active. And then you add all contributions to find the final answer. So in this circuit, we have two sources. We have one source over here, the voltage source, and we have a current source pointing down over here. We need to find VO, right? So what we're going to use is superposition. So let's say, let's kill to keep 1, right? So we're getting rid of this guy. The way we kill a current source is we open it. The way we kill a voltage source is to short it. So we're going to kill it by opening it. The circuit redrawn is going to look like this. And remember, VO is over here. This is 2 ohms. There's no current flowing here. This is 6 ohms. We have a 10-volt source. VO is therefore equal to, it's a simple voltage divider, 10 volts times 2 ohms, if we have this as ground, times 2 ohms over 6 plus 2 ohms, the sum of both the resistors. So this comes out to be 2.5 volts. Let's call this VO dash because it's not the same thing as VO. We're going to find what VO is at the end. Now let's kill 1. So we kill the voltage source and we keep the current source. So we get rid of the voltage source. The way we get rid of a voltage source is by shorting it. We still have this resistor over here. We have the current source going down here. And here is VO. So this is a 1 amp current source. If you look at the question again, it was 1 amps pointing downwards. We got rid of this guy over here. So let's call this VO dash dash because it's not the same thing as VO. This is 6 ohms. Here's 2 ohms. All right. So the solution to the circuit is fairly easy. First, we can find Ix using a current divider. Ix is equal to 1 amps times the opposite resistance over the sum of the resistors. So Ix is 6 over 8 amps. Okay, now let's try to find what the voltage drop across the 2 ohm resistor is. So the current's entering over here and exit, it always needs to exit from the negative terminal. So the voltage across this is going to be, in this sense, is going to be Ix times 2 ohms, which comes out to be 6 over 8 times 2, which is 12 over 8 or 1.5 volts. However, you might notice that in this convention, this is opposite to the output voltage we want to find, right? They're exactly opposite. Therefore, VO dash dash is just going to be the negative of that calculation we did. So negative 1.5 volts. All right, the final step would be to add, let's say the final step to find VO in this circuit is to add the individual contributions of each source. So VO is equal to VO dash plus VO dash dash, which we found were, so VO dash dash is negative 1.5 volts and VO dash was 2.5 volts. So 2.5 minus 1.5 volts, that's going to give us 1 volt. So the answer to this question is 1 volt. Okay, so here's a way you can see all the steps. We're trying to find this voltage. We kept one and killed the other. Then we kept the other and killed the first one. And then we added both of them, 2.5 and 1.5, to find out the final answer. All right, let's move on to Thevenin and Norton theorem. So in this is a very um, this question requires you to reduce the circuit into either something like this, which we call the Thevenin equivalent, or the Norton equivalent, which looks like this: a current source in parallel with a resistor. In both cases, the resistance is the same. It's called RTH. This is the Norton equivalent circuit. So the question is asking us to reduce the circuit we're given into either one of these. So another important thing to note is that these two are completely equal to each other. There's if I add something over here like a resistor, it's gonna be the same if I add something over here. The circuit's gonna behave the same way. So another way to think of this is what your source transformation is. So a source transformation says that a voltage source in series with a resistor is the same thing as a current source in parallel with a resistor, right? So over here, if we look at this over here, we have a current source in parallel with a resistor, right? But we don't have a voltage source in series with a resistor. But we want to combine these resistors in series or parallel. Over here, we have two resistances in parallel, but here we don't have this resistance is not in series with anything. So we cannot combine it. Therefore, we're going to do a source transformation. So let's redraw the circuit with the source transformation. The current source now becomes a voltage. So the voltage source so let's say that the terminals were over here and here. Now that's going to look like this over here, the Thevenin equivalent. So it's going to look like this going up. Now we have resistor, and then we have another voltage source. We can simplify those two resistors to be 6 parallel 8. This is going to be 6 ohms. This voltage source is now going to have a value of 6 times 9. So if we look over here, the current source had a value of 9. The voltage source, so V is equal to IR, or VTH is equal to ISCR. So um, VOC is equal to ISCR. So this is going to be equal to the value of the current that was on the source times the resistor. So 9 times 6 is 54 volts, right? So we have this circuit over here. These two voltage sources are in series, and these two resistors are in series. So we can simplify it into this. This is your Thevenin equivalent. You have 59 volts here. You have 6 plus 6 parallel 8. So I don't have my calculator with me right now, but whatever 6 parallel 8 is, you're going to want to add that to 6. That's going to be your Norton equivalent. Sorry, that's going to be your Thevenin resistance. Yep. So it looks like the answers to this is 9.43 ohms. That's your Thevenin circuit. If they ask you for a Norton circuit, it's going to be like this. The resistance is still the same. RTH is equal to 9.43 ohms. Here are your terminals, right? And this is going to have the value of VOC over RTH. So ISC is going to be equal to 59 over 9.43, whatever that is in amps. All right. Okay. This is what I expect you to know for your midterm. These are the major concepts. I'm going to go over some extra concepts that may or may not show up in your midterm, depending on how late you are into the semester. So let's quickly go over phasor. So um, phasors are a way we represent time varying voltages that are also sinusoidal. These help us to solve and find the forced answer to to a circuit. A forced answer is basically what it's gonna look like at steady state. A steady state means after the circuit's been left running for a long time. So if your circuit has any sources that are AC sources, so a cosine wave, you might want to use phasors to solve your circuit because it makes solving the circuit much easier. All right, let's see. So the basic gist of it is that if you have a voltage as given in this question, V of t is a time varying cosine 820t. So this 820 is what our omega is, the angular frequency. Minus 30 degrees is the phase shift from a default phase of 0, right? So how do we express this as a phasor? So one thing to note is that we don't, a phasor has a magnitude and an angle, and the magnitude is always a positive number. So over here, we know that the magnitude of this cosine, if we just draw out a cosine wave, we know that the magnitude is going to be whatever coefficient is before the cosine. So it's going to be having a peak of 5.7. So magnitude of V of t is 5.7. Let's write that in a better manner, actually. The magnitude of the phasor of V is 5.7. How do we find the angle? Well, we have to account for this negative sign. We're going to put that into the argument of the cosine. So we're going to use this identity over here. There's these two identities. If you're given a sign, if you use this identity, you can go back to a cosine. Or if you're given a negative cosine, you can make it a positive cosine. So let's rewrite V of t. V of t is equal to 5.7 cosine 820t minus 30 degrees plus or minus 180 degrees. Now, plus or minus 180 degrees because in the complex domain, if we move 180 degrees, it doesn't matter if we are moving a negative 180 degrees or a positive 180 degrees, we're going to end up at the same point. What matters is that this angle over here needs to be between, it needs to be between um, negative 180 and positive 180 degrees. So we're going to choose the value of positive or negative 180 to such that we keep this between these limits. So if I do choose negative 180, then this phi is going to be negative 210 degrees. But if I choose positive 180, it's going to be 150 degrees. Sorry, negative 150 degrees, which is in my range. Sorry, wait, let me think of this. Uh, sorry, positive 150 degrees. So if you think about it in the complex plane or in a unit circle, um, 150 degrees is like somewhere over here, right? And if I go negative 210 degrees in the other direction, I still end up at the same point. So both of these are talking about the same phase angle. But we're going to use positive 150 so that it conforms to the limits between negative 180 and positive 180, right? So let me scroll down a little and rewrite what VFT is. Just following the steps. VFT is 5.7 cosine 820t plus 150 degrees. So the question said it's this. This is another way of writing the same thing. And then the phasor is an even better way to write the same thing. It gets rid of the frequency dependent information. So um, we assume that the for omega is equal to 820 radians per second. The phasor of V is 5.7 magnitude, and the angle of V is 150 degrees. So together, we're going to write V is equal to 5.7 angle 150. And if we go back to the question, you notice that the question said that V of t is expressed in microvolts. You have to maintain those units. You're going to say microvolts at the end. All right. So now that we introduced ourselves to phasors, let's go on and try to solve some Thevenin and Norton questions with phasors. So if you're given a circuit like this, you've noticed that now instead of just a combination of resistors, we also have a combination of what do you call inductors and capacitors that we have to account for. So we can't use the same methods that we were using before. I think I'm missing some information in this question. Let's see. Right. The question's supposed to say that I1S is equal to the phasor I1S is equal to 5 angle 45 degrees. And this circuit is operating at a frequency of 100 radians per second. All right, let's see. Let's try to simplify this circuit, okay? So over here you have the um, these two in series, and you also have this capacitor and resistance in series. So let's first combine things in series. So when we are combining a resistor and capacitor, it's now going to have a complex magnitude for its for its impedance. So we can't draw a resistor or a capacitor. We're going to draw a box. That box is going to have 3 ohm plus negative J7. So 3 minus J7 ohms of impedance. Likewise, over here, we're going to combine the inductor and the resistor. It's going to have 1 plus J5 ohms of resistance, right? Because we're adding the 1 ohm and the 5J inductor. And here are the terminals. So now we have our current source in parallel with an impedance. So we can do source transformation. Source transform. So once we do the source transformation, we're going to get a voltage source in series. Now you don't need to place the box at the top or the bottom. The box is still going to have the same resistance or impedance, 3 minus J7. We had another box over here that had 1 plus J5 ohms. Our terminals are over here. And now we need to find out the value of this. So the value of that is going to be I1S times whatever was in parallel with that. So 3 minus J7, 3 minus J7. So you're going to plug this into the calculator. You're going to plug exactly the 5 angle 45 degrees times 3 minus J7 into your calculator. And whatever the answer to that is, it's going to be the value of the voltage over here. So if I plug that into my calculator, I get 38.1 angle negative 21.8 degrees. So that's my, let's just call it V1. So that's the value of V1. Okay, so we know what V1 is. These two resistances over here can be added in series because they are in series. Let's make some space over here to draw the final circuit. So the final circuit is going to look like this. See a Thevenin circuit. It's gonna have V1 is equal to what we found it to be 38.1 angle negative 21.8 degrees. The this resistance is gonna be the series combination of here this and this. So that's 1 and 3 add to 4. Plus J5 minus J7 that adds to minus 2J, and that's in ohms. So this is your Thevenin equivalent. They ask you to find the Norton equivalent. It's going to be the same thing. It's just that now the box is in parallel and the terminals are off to the side over here. So 4 minus 2J stays the same. That's the value of the impedance in the box. This is going to have the value of V1 over 4 minus 2J, whatever that is. So if you plug that into a calculator, V1 is this 38.1 angle 28, 21.8, right? So if you plug that into a calculator, you're gonna get 8.51 angle 4.76 degrees in amps. Okay, so it's important to that you know how to use your calculator and know how to use it well so that you can do these complex calculations for your phasor analysis. Let's move on to first order transient. You may want to double check if phasors and first order transients or second order transients are showing up in this midterm for you. But I just want to go over all the topics that could possibly show up in a midterm. All right, let's get on with it. So a first order transient is basically a circuit that contains only one reactive element. A reactive element is known as a capacitor or an inductor. So in this circuit, we have um, three resistors, one, two, three, but we have one capacitor that's VC, that's over here, the 50 microfarad capacitance between these and these two ends. So we have this is a first order transient because we have only one reactive element. If we had two reactive elements, like over here, we have an inductor and we have a capacitor, that's a second order transient. So the way we would solve a first order transient is I've written it down over here. First we do uh if you think about it, let's actually work through this step by step. We need to find what's the charge on the capacitor before the switch turned on. So we denote that by T of 0 minus. That's saying, oh, let's draw the circuit before the switch turned on, and let's assume that the switch has been off for a long time, and let's try to figure out what the charge on the capacitor was back then, was before the switch turned on. So we have the 2 kilo ohms. The switch is open. So let me zoom in over here for you. The switch is open at first. So we're going to ignore that it exists. There's no current flowing through it. But we have the other 2 kilo ohm, and then we have the 6 kilo ohm over here. Capacitor, right? So let's try to find what the VC of 0 minus is. 226. So in steady state, we can replace a capacitor with open terminals, right? So if we want to find this voltage, we're just going to do a voltage divider off of what the source is at. The source is at 8 volts. So VC of 0 minus is equal to 8 volts times 8, which is the sum of these two, over 10, which is the sum of all three of these resistors. So that's going to give you 6.4 volts. So VC of 0 minus is 6.4 volts, right? Okay. All right, great. Let's now see what happens when the circuit is at infinity, right? So we let the circuit we close the switch and we let the circuit stabilize itself. What's going to happen is because the switch is closed over here, and we still have a resistor over here, but since the switch is closed, this is a short circuit, right? So this resistor over here, which was 2 ohms, 2 kilo ohms over here, that got shorted, right? So so this resistor almost doesn't exist because there's no current flowing in there. So this is our new circuit, this simplified circuit. Again, we are at steady state because we have let the circuit stabilize itself. So after a long time, we say that the capacitor can be replaced by open terminals, right? So we have the 6 kilo ohms over here, 6 kilo ohms, 8 volts here. So now what's VC of infinity? VC of infinity is going to be the 8 volts divided by 6 over 6 plus 2, so 8. So that's going to be 6 volts. So we see that we started off at 6.4 volts, but we're ending up at 6 volts. So if I draw the diagram, right, we have T, we have VC of T at before the switch closed. So for a long time, it was at 6.4 volts. Okay, let me write this in a better fashion. 6.4 volts. But after we let it stabilize for a long time, it reaches 6 volts. So the value of the voltage across the capacitor drops. The reason it drops and how much it drops is it drops in a fashion like this because the drop is a solution of a differential equation, which we're going to solve right now, right? So how do we find the solution of a first order differential equation? The solution of a first order differential equation is always of the form. So let's say solution is always of the form a plus b, sorry, a e to the power minus st, where s is your natural frequency. We need to find what s is, right? Plus b, which is a constant, right? And now let's try to apply some of these initial conditions to find out what a and b are, okay? So this can also be written as a e to the power minus t over tau, okay? Plus b. Let's see what tau is. So tau is, if you have an inductor in your circuit, it's gonna be L over RTH. And if you have a capacitor in your circuit, it's going to be C times RTH. Okay? In this case, we're going to say C times RTH. When do we take this RTH? We take it at this moment when t is equal to infinity. Okay? So let's try to apply some of the initial conditions. So we know V of 0 minus is going to be 6.4 volts, and that is equal to e to the power minus st plus b, right? T is equal to 0, right? And e to the power 0 is going to be 1. So that's going to be a plus b. So we know a plus b is 6.4 volts. Okay, how about at infinity? V at infinity is going to be, we found it to be 6 volts, right? So we're going to plug in a e to the power minus s negative infinity. So e to the power negative infinity is going to go away. It's going to go to 0, right? So all we're left is with B. So we know B is equal to 6 volts. So what is A equal to? A is equal to the difference between 6.4 and B. So it's going to be 0.4 volts. So we know our constants, right? All we need to find is tau now. So we know the solution is B 6 plus 0.4 e to the power minus t over tau. Tau is equal to C times RTH. C was given in the question. If we look at the circuit, it's 50 microfarads. So 50 into 10 power minus 6. right? And then we have RTH, which we find over here, right? If we look into these terminals, we kill this source to find RTH. We kill the source. To kill a voltage source, we short it. So imagine this voltage source over here didn't exist. So let me just redraw the circuit. It's going to look like this. We have 6 kilo ohms over here, and we have 2 kilo ohms over here, right? If we look back at this, 6K that way and 2K the other way. So RTH is 6K parallel to 2K, which is RTH is equal to 6K parallel to 2K, which is equal to 1.5 kilo ohms. So we're going to multiply our capacitance with 1.5 into 10 to the power minus 3. The answer to that is 75 into 10 to the power negative 3, right? So that's what you're going to put in for tau. So our final solution is 6 plus 0.4 e to the power negative t over 75 into 10 to the power negative 3. Okay, the last thing I wanted to go over was second order transients. Always remember that second order transients are going to have this form for their solution. There are more specific forms for a solution if the circuit is underdamped, overdamped, or critically damped. Okay, so we're gonna go over first how to solve this question over here. So they've given you the governing equation. This governing equation just pops out of a doing a KVL and then doing a derivative on that KVL. So we're not going to go over the derivation over here. They've given you the equation you have. So let's write down this equation over here. Let's replace our values for R and L, right? So if we know that the solution has this form, right? So let's plug in one of the solutions. So K e to the power S T. The second derivative of that is going to be S square K e to the power ST. And then you have R over L. R is 2, L is 8, so you're going to have 1/4. So S, K, E, S, T. So what I'm doing is like I'm plugging in I of t is equal to K e to the ST. The second derivative of that is S square K e to the ST. The first derivative is going to be S K e to the ST plus 1 over LC. That's 1 over 8 times 2, so 1 over 16. K to the power st. This is equal to 0. Okay? So notice that this is the common factor between all of this. So we can bring all of this over to the other side, multiplied by 0, so it's going to disappear. So what we're going to be left with is called a characteristic equation. Okay? And you can come to this conclusion just by replacing your values into this, calling this s square, calling this s, and calling this constant, so 1. Okay? So you have your characteristic equation. So you're going to try and use the quadratic formula to find the solution to this. So the solution, if I plug this into my calculator, is going to be, for the sake of time, I'm going to skip the calculations. It's going to be a complex number. It's going to be negative 0.125 plus or minus 0.217. Okay, this is your solution for S. I believe that, yeah. Yeah, that's your solution for S. Okay, so mm, 5 inverse. All right. Another thing we could note from this characteristic equation is that the term that's over here is known as omega n squared, which is the natural frequency squared. The term that's the coefficient over here, this 1 over 4, is going to be called 2 zeta omega n. Okay? Just by equating the terms, I can say that omega n is equal to 1/4 because I'm taking the square root of 1 over 16, right? So 2 zeta omega n is equal to 1/4. I already know omega n is 1/4, right? So 2 zeta is equal to 1. 2 times zeta is equal to 1. So zeta is equal to 1 over 2 or 0.5. So when zeta is less than 0.5, so let me make some more space. When zeta is less than 0, when zeta is less than 1, we call it underdamped. When zeta is equal to 1, we call it critically damped. And when zeta is more than 1, we call it overdamped. And, and the solution to all of these three look slightly different. I have the some useful equations over here that tell you about how these solutions look. So over here you have the overdamped case, you just have the standard solution. In the critically damped case, you have this extra t term multiplied by the second exponent, and in the underdamped case, you have a real exponential and you have the sum of complex cosines. Sorry, the sum of two complex exponentials, which is this over here. Um, I don't expect that you are going to see second order transients this early into the semester, but if you do have any questions, you can please reach out to me at the tutoring center over here. We are at ECG 104 and ECG 152. The engineering courses like electrical engineering and circuits are done at ECG 152. These QR codes have more information on about our program, about our Instagram, our website, and our YouTube. This video is also going to be uploaded to YouTube for your reference. And yeah, I hope to see you there soon. And thank you for attending today's review session.